asking, is everyone there? Are you ready?
Yes.
Okay. Do you want to show yourself or you want to be hidden? Okay, thank you. Good. I mean, I'm still seeing people joining in.
Oh, yeah.
But I think I will start with saying a little bit about Steve Borgatti. So I don't remember when we first met Steve, but it's a while ago. So Steve is a chair of management at Gatton College Business and Economics at the University of Kentucky, which is in Lexington, which is in the, I would say, the middle of the US, a bit to the east side. He has published in over 100 papers, peer-reviewed papers, many in social networks, also one in social networks in science, which actually is one of the things I should share with you. And Steve, you have over 70,000 Google Scholar. Okay, I have 5 more people joining in now.
Yeah.
So let me just give a moment. Over 70,000 Google Scholar citations, which is sort of the currency in academia to see how good people are, and 70,000 is a lot. And he is the co-author of USINET. For those that did sociology, you might have seen USINET taught by Mario last year. So I would say he's the person programming most of the things. I think all of it, right?
Yes, all of it. Yeah.
All of it. So Martin is more in charge of documenting things. And you have also been 2 times INSNA president, which is the big social network community. So, sorry, I'm keep on clicking on people that have to join, so it's just like multitasking.
Not a problem.
So the reason why I thought it was interesting is because Steve has also not only taught a lot of social network courses, but has worked quite extensively on centrality measures. One of the biggest papers, one of the most cited papers, is the 2005 one on flows in centrality. So I think it was great that Steve would be able to join in this. Steve, I would say start sharing your screen, and okay. You can start. I will, in the meantime, just keep accepting people as we go.
All right. Let me move things around here.
So now we can see your Zoom.
Yeah, it's pretty funny. And a presentation, which you can put in presentation mode. I have to admit, very plain slides.
That's okay. It's about the content. So, okay. So, Steve, go ahead. I'm going to put myself in mute.
Okay, great. Let me just move another box here. All right. So, welcome everyone. We're going to talk about centrality, and sort of the intuitive idea behind centrality is that being in the center of some kind of system. And I just have to say, I'm looking out my window at the moment, and the campus now has robots that deliver packages, food, and things all over campus, and it's hysterical to watch them walk, basically driving along the campus. Anyway, so if you have any kind of a system, like a road system or an electrical system, the center is often important. And in social systems, it may be that it's being in the center that makes a node important. But it could also be that actually the reason why they're in the center is because they're important for other reasons. So the causality is unclear, but either way, we're interested in understanding which nodes in a network are central and which ones aren't. So one way to think about what centrality is that it's a measure of structural importance. Given just the network, you don't know anything about the nodes, you don't know their names, characteristics, we just have ties among them. Can we look at that structure and say something about which are the important nodes? And there will be many different ways in which a node could be important. I mean, just looking at this one, J leaps out at me because they have so many ties. D is also like that in a different way. D is kind of the center of a little group, whereas J is not so much the center of a group, but they do have many connections. And then obviously I and H seem very important in a different way because they're spanning the boundaries between the group on the right and the group on the left. And if they were to be removed, it would really change our impression of the network. In fact, it would be just two separate little clumps. So another way to think about centrality is in terms of a node's contribution to the network structure. So whatever it is that we're thinking about what that network structure is, it's going to depend heavily on a few nodes that somehow make it happen. In this case, we have a structure that is kind of a bow tie structure. There's a section on the right, a section on the left, and then a weak connection between them. And so these nodes I and H make a huge contribution to the global connectedness of the network. Oh, people should feel free to ask questions. Philip can tell me when the question's been asked. So another way of thinking about centrality that's sort of maybe more directly sociological is as social capital. So social capital is one of these concepts that is an export from network analysis, although the term goes back very far. It goes back to the 1930s. But the idea is that if you are central in the network, that this is social capital for you, that there are advantages to being central, and it's just a matter of how you might be able to exploit that. So, for example, you might be more likely to catch something that's moving through the network, such as ideas or news, information, and so on. You're likely to catch it early if you're very central, and that's advantageous because you get it before everybody else knows it. It's like hearing a joke and then passing it on. You don't want to pass on the joke if everybody's already heard it. You may be able to control information that flows through the network because of your position. It may be that your position, kind of like I and H here, are kind of indispensable to the network. If they leave, it changes the network massively. And so they may be able to extort the others by saying, look, if you don't do what I say, I'm going to leave this network. And of course, there's many negative consequences to being highly central. One of them is that something that might be flowing through the network could be viruses. And so you'll catch it early and you'll catch that virus before the vaccine's been developed. And that's really not the best situation. You might also be subject to more conflicting influences. So if I go back over here and I look at node D here, it seems in such a good position. They're really well connected to these other people who they may have different political beliefs, for example, from each other. And so D may be pushed and pulled among their friends, among his or her friends. And also these people here may act as a brake on person D, so that if D wants to change the way their identity, the way they do things, they've got this little group here that maybe is going to enforce some behavioral norms. It's like, we know you as this and we want you to stay that way. So it does have negative consequences as well. Okay, so let's get to the meat of things and talk about different ways in which nodes can be central. And we refer to them as different measures, but sometimes people get the wrong idea about measures. They think, there's a single thing, such as maybe the wealth of a country, and there are multiple measures for measuring that one concept. But in the case of centrality, these different measures actually capture different aspects of centrality, different ways of being central. They're actually different ideas. So the simplest measure of centrality, some might even argue that it's not a measure of centrality because it is so local, is simply to count the number of nodes, the number of ties that a node has. So if you think about it in terms of friendship, we've got a friendship network, and you have some people that have a lot of friends. There are certain advantages, right? So there's a chance if you have all these friends that somebody can pick you up from the airport, that somebody can fix your computer problem, somebody can help you move to a new location. You have this kind of support that's there, that's in a material sense. You can have resources. There's also, of course, the emotional companionship, entertainment support that's provided by having friends. Also, having a lot of friends means more exposure to different ideas, ways of doing things. It's kind of it's a resource in another way, in that you become broader as a result of your friends. You don't have to read everything yourself. You don't have to learn everything yourself. Your friends can simply tell you about things that you didn't know before, such as a new restaurant opening up. And as sort of I alluded to before, of course, having too many friends could be exhausting, and they may make contradictory demands and so on. So this is a very simple concept, but it has a lot of effect on things. A very early study in network analysis was one that showed that people who were very central in a nursing home, so a retirement home for people with illnesses and so on, so people in their 70s and 80s, that people who are more central in the friendship network of the nursing home require fewer doctor visits. Another study, much more recent, showed that if you bring people into a laboratory and you inject everybody with the cold virus, so everybody's equally exposed to the cold virus, it turns out that the people who have more friends are able to fight the virus and don't actually come down with the cold. So just a variety of different things that degree centrality has been shown to affect. So we could think of degree centrality clearly as social capital. It's just very obvious. It is a potential for influencing others. If you imagine a trust network and you have many people who trust you, you have the ability to influence many people. At the same time, typically, if these are bidirectional ties, then if you have many trust ties, you trust many people, and so you are influenced by many people, which could actually get quite complicated. And of course, it need not be that degree itself is what's making you important. Again, as I mentioned at the beginning, it could be that you're important in some other way. Perhaps in a male-dominated organization, you are male. That gives you a greater centrality. That gives you people are more likely to want to have ties with you, trust you, things like that. Now, the thing about degree centrality is that it treats all of your friends equally. So that may not be exactly what you want. It may be that it makes more sense to weight the people who are well connected more. So if you think, for example, of F in this picture here, and you compare them with A over on the right, they both have only one friend. So they're equal in terms of degree centrality. But F's one friend is themselves kind of an outlier who does not have a lot of connections. On the other hand, A is connected to B, who does have more connections. So it seems like you would like somehow to give A more centrality points than F because they're connected to more connected people. So basically what we can do is, if we think about how degree centrality might be calculated, here is the adjacency network, the adjacency matrix for this network down below here. So A has a tie with B, so there's a 1 there. A does not have a tie with anybody else, so they're all zeros there. And to calculate degree, we can simply take the row sums and we get the degree vector there, and we see that B has a lot of ties and that D has a lot of ties. But to weight people by how well connected they are, we could simply take the weighted sum. So I take this one here and I say, well, how much is that connection there worth? Well, that's a connection to B. B has 3 friends, so I will 3. Now we can look at B, or let's go to C since there's only 2 ties. C is connected to B and D. How much were B and D worth? Well, B was connected to 3 nodes and D was connected to 3 nodes. So that's 3 plus 3 is 6. So if we're calculating this measure again, we get a 6 here for C, and so on. And once we look at this in this weighted way, we see that D gets slightly more points than anybody else. Before, D and B had the same number of points, but it's saying no. If you look at the pattern of who they're connected to, D's got this connection to somebody who's not well connected, and that reduces. Oh, sorry. Well, actually, that's not true, is it? No. I guess D is just a little bit closer to all of these over here. There's more people within 2 links of D. All right, but if we can do that process of weighting, then why not do it again? So here we have our network matrix. We take the row sums, we get degree. Then we take the weighted sums where we're weighting by this degree vector, and we get the second degree. So the second iteration of degree. And then we could do it again. So when I calculate the row sum here, I'm weighting B by B's previous score, which is a 6. And so A gets a 6 for that. And we see this, and then we can do it again and again and again. And of course, what we see is that the numbers just keep getting bigger and bigger. But the ratios, the intervals between them, start stabilizing. And we can tell that by simply taking percentages. So if we just take the sum of D1, that's 12, and 8.3 here is just 1 divided by 12. And so here we've got the percentage of the total, and these are varying, but after a while, they all start looking like they're around 10.5, something like that, or 10.4, and the 24 settle down. And so this is kind of a long-term equilibrium steady state score. And in that one, you can see that A gets 10 points, and F only gets 5.7 or 6 points. So it's really weighting A quite a bit more because of being connected closely to this cluster of well-connected people. So let me just pause there and see if anybody had any questions on that. Okay, so what does this do? Well, it turns out that this process of iterating degree until it stops changing is a method of calculating something called an eigenvector. And an eigenvector is a vector when you multiply it by a matrix, you pre-multiply it by a matrix, you get the vector back again, aside from a proportionality constant. So if we write that out in a different way, what this says is that if we're looking at the eigenvector score for node I, it's equal to the eigenvector scores of all of I's friends, because A sub ij is a 1 or a 0, indicating whether I has a tie to J or not. So when it's a 0, this is going to be zeroed out. So when it's a 1, that means that J is a friend of I. We multiply 1 times the score of J, and we sum it all up. We divide by a constant lambda here, and we get the score of I. So what that means is that I score is literally proportional to the sum of I's friends' scores. Okay, so calculating, you can see that this is kind of a weird thing to calculate, because in order to calculate the score, you have to already know the score. But as I showed up here, there are ways of doing it, such as this iterative method here. So this eigenvector then provides an interesting possibility for being a measure of centrality, because it really captures the idea of being well connected to people who are themselves well connected. And so we typically think of that as some kind of measure of status. It's particularly evident, I'll come back to that slide in a moment, in say something like a playground situation. You have kids, maybe you have many friends if you're in a school, but if they are all outcasts, this really does not do you any good. In fact, it's probably bad for you to be connected to the people that are considered outcasts. But you could have just one friend, and if that friend is the most popular kid in school, then your status is probably going to be okay. Right? So it's like you bask in the reflected glory of someone else that you're well connected to. And people, when they see you, they think of this very well connected person. And so that transfers to you. Looking at this diagram here, if we think about, okay, who has the highest eigenvector centrality, it's node D here. And node D has 1, 2, 3, 4, 5, 6 ties. Node J has 1, 2, 3, 4, 5, 6, 7 ties. So J has more ties, but they are to people who are not as well connected. Whereas D is connected to people like B, who have 4 ties, and G, who have 5 ties, and F, who has 4 ties, and so on. And so D gets a slightly bigger score. One thought is that this means that having a high eigenvector score provides a measure of your exposure in the network. So think, for example, of nodes S over here and compare them with node R. And let's assume that this is a sexual network and that there is some sexually transmitted disease that's going through this network. And R and S are both following rationality and saying, well, you should only have one partner and that will help protect you. The trouble is that R is having sex with somebody who is having sex with lots of other people, and that puts them at much higher risk than S, whose partner is not really, doesn't have a lot of partners themselves. Right? So in a way, H is kind of a super spreader here. So the thought is, okay, this provides a better measure of the extent to which the node may be exposed to what's flowing through the network, which in most situations is a good thing, because there's gossip flowing through the network, there's news, there's information about new ways of doing things, new products, and so on. And so that would be valuable. There's also the sense, and you can just compare the J and D here, that the eigenvector is often going to indicate that you're part of a group, because one of the ways in which your friends can be well connected is by being connected to your other friends. And there are certain benefits to being part of a tightly knit group. You might feel like you're an in crowd, you're a core, you're a dominant coalition, you're supported, you have an identity as a set of friends. Now, that actually also introduces an issue with it. So in terms of the exposure that you have, it's really clear that R here, wherever my cursor has gone, R has more exposure than S because of the connection to H. But whether D has more exposure to diverse ideas than J does is open to question, because in part, by being connected to these well-connected people, D isn't really getting more exposure because D is already connected to these people. So, the fact that D is connected to G and G has ties to E and to B and to F doesn't add anything more to D, because D was already connected to E and to B and to F. So the exposure idea doesn't always work. I'll pause in case there's a question there. Okay, so.
Wait, I think we have a question.
Oh, you do? Okay.
Francesca? Or not? Or maybe I was just... Everything okay? Everyone okay? No questions?
No, sorry.
Oh, okay, sorry. Okay.
All right, I will proceed. So what we saw so far was essentially variations on the number of people you're connected to, right? So there's simple degree, number of friends you have. Then we said, well, wait a minute, let's just take into account the number of friends they have. And then we said, well, let's keep doing that. And that led us to this eigenvector concept, where you are literally as central as the sum of your friends' centralities. But now let's move to a different concept. And this concept is closeness. And closeness has to do with distance in the network. So I'm guessing that you already know that there is this concept of geodesic distance, and that what it means is that there are many paths from one place to another, but there are certain paths that are shorter than others, and we refer to the length of the shortest path between two people as the geodesic, or literally as the distance, the geodesic distance. So for example, to get from A to G, one could go A to B to C to E to F to G, but there's a shorter path, which is to go to A to B and then straight to E. And so the length of this path, which is 4 links long, is the geodesic distance between A and G. If we calculate the distance between every pair of nodes, we can record that in a matrix like this. And you can see that A is close to some, but far from G. And we could simply sum this up. We can take the row sums, just as we did with degree, and get the overall distance that A is from everybody else. It's basically, it's how many steps removed you are from everyone in the network. And clearly this is a kind of inverse measure of centrality, because if you have a small sum, like person E, it means that you are more central. You are not very far from anyone. In fact, E is only 2 links away from anybody in the network, and is also 1 link away from several others. It's a very small sum here. Whereas G is the farthest from everybody, total of 17 steps away from everybody else. This measure, and I'll come back to like what it's useful for, really was born of these experiments that were done at MIT in the 1950s by Bavelas and his student Levitt. And they were studying communication structures, and they were interested in which kind of communication structure leads to more efficient problem solving. So you have these different structures, such as this, they called it a wheel, I would call it a star, a circle over here, and so on. And the way they actually implemented this in a study was to have people come into the laboratory and they would sit at cubicles. And if you were C, you would discover that your cubicle has 4 holes in the wall through which you could send messages. And if you were C in this experiment over here, you would find that there were 2 holes in the wall through which you could send messages. And what happens is that each person is given a certain amount of information that's unique to them. And in order to solve the puzzle, solve the task, they have to combine each of those diverse pieces of information, work out the solution to the puzzle, and then make sure that everybody has the solution. And so, for example, in the case of the wheel, this is a very simple kind of structure. What happens is in the very first round, everybody furiously writes down the information that they have. So B sends their information to C. Simultaneously, whoever that is, E sends to C, D sends to C, A sends to C, And at the end of the first round, and it doesn't matter who C sends to, and since it's physical writing, C could only send to one person, by the way. C knows the answer. C's got the information from everybody, including their own information. So C could then send a message to A. That takes a unit of time. So now we're at 2 units of time. And then they could send a message to B with the answer, that's 3, and then to E, that's 4, and then finally to D, and that's 5. So it takes 5 units of time to complete the puzzle if C even gets it right. So, and each of these structures has this kind of characteristic, what is the minimum possible if they do everything perfectly? When you look at the results, they're listed here. Here's the row called time is on average, how long did it take to solve the puzzle? And for the wheel structure and the Y structure, it was around 35 time units, which is low. And the other two were about 50, significantly higher. So these kinds of structures take longer to solve the puzzles, but also they didn't always solve them right. And so we can count the number of times that they get it wrong. And here they're mostly similar, except that the circle tends to screw up the most. And then in terms of efficiency, the number of messages that they had to write to each other, because they would write something and say, oh, no, I was wrong about that. Let me take that back. And they said, write another message and so on. It turns out that the 3 on the right are pretty efficient, but again, the circle was very inefficient. And what Barvelos and Levitt concluded from this is that structures, communication structures, have a natural integrator of information. So they would look at C in the wheel here and say, well, that's the natural integrator. And then what determines how well the wheel does in solving puzzles is how far away everybody is to the natural integrator. And in this case, everybody's directly connected to the natural integrator, so this can solve the puzzle quickly. The trouble with the circle is that there is no natural integrator, and whichever we could pick one. So C could send out a message to everybody that says, I am your leader. Send me the information, I will tell you the answer. But people are far away from that integrator. And so it takes a long time to get things done. So the way they conceived of it, it was distance from one individual. That's kind of the leader. The modern concept of closeness is more distance from everybody else. Oops, that is not where I expected to go. So I am missing a slide, I am afraid, here. But the idea is that not only is a structure going to be good at solving things if everybody is close to everybody else, but also an individual like E is going to be advantaged if they are near everybody else. And as I mentioned before, that nearness means that things traveling through the network are likely to reach them, because as you know, if D might send information to C, they might not. And then C might send it to E, they might not. And long chains are less likely to complete. So if you're close to many people, you're more likely to receive things. And of course, we can think of distance as kind of the time until arrival of something moving to the network. So it only takes 2 units of time to go from D to E, but it takes 5 units of time, 1, 2, 3, 4 units of time to get all the way to G. So by the time G hears about it, it's no longer that interesting. Okay, so let me click here. So let's now move on to a concept. By the way, I love the copyright on my slides. Tua 021. I just have no idea. Is that true in all these? No, it's only in that slide. Interesting. So we're going to now look at a measure that's considerably more complicated, difficult to explain, but that shares some of the characteristics of this closeness centrality, and also shares some of the characteristics of the degree centrality and eigenvector centrality. So it kind of puts it all together. So it's defined as follows. First of all, I'm using whatever this letter is. What is that letter in Greek? Philip usually knows these things. Anyway, I'm using this as a vector, and that vector is the centrality of each node. We want to calculate that, and here we have a matrix equation for it. And you notice that at the end of this matrix equation, there's a 1 here. This is a column of 1s. So we're going to be multiplying this thing, which is a matrix, by a column of 1s, which means that we're going to be taking the row sums of this mess. Okay, that's what happens when you do a matrix multiplication, multiplied by a column of 1s, you get the row sums. Let's assume that R is the network. It's the matrix that represents the network. This whole thing, well, beta here is a constant, and we have to choose that constant. We'll come back to that, how we choose that. This is the identity matrix. So it's a matrix minus a constant times our data matrix. Then we're taking the inverse of that, and then we're multiplying it by the data matrix. Again, that gives another matrix, another node by node matrix, and then we're going to take the row sums of that. Okay, but now what is this matrix that I'm showing here, this big complicated thing? Well, under the right conditions, we can rewrite this as an infinite expansion. And the condition is that when beta is smaller than 1 over lambda, and this lambda is the lambda that we saw here. It is the eigenvalue of the principal eigenvector of the matrix. So before we just kind of dismiss this as kind of a proportionality constant, and really it is just that. It doesn't have much significance of its own, but we're going to make use of it over here. And when beta is smaller than 1 over the largest eigenvalue of the matrix, then this matrix equation here works out to be this infinite series. Now, what is this? So it's beta to the 0 times r to the first. Well, r is the network matrix. R to the first means just R, so it's just the network matrix. Beta to the 0, no matter what beta is just 1. So this first term is just the adjacency matrix of the network. The next term is beta times R squared. So what is R squared? Well, actually, I think I probably have a slide for that. Yes, I do. So R squared is literally the adjacency matrix multiplied by itself. And it's known that R squared gives you the number of two-step, I'll use this loosely, I'll say paths, connecting each node to every other. So in other words, it's a node by node matrix. And for the cell ij, it gives the number of two-step paths that go from I to j. Now, they're not actually paths. Technically, they are walks. I don't know if you know the distinction, but it's not going to be important for what we're talking about here. So I won't bring it up. But we'll just think of it as two-step connections. R cubed literally gives, for the ijth cell, it gives the number of paths of length 3, of exactly length 3, that go from I to j. Okay, and so the same with R4 out to infinity. All right, so now the infinity part, that gets a little confusing because you think, well, if the network only has, say, 10 nodes, how can you have a path that is of infinite length? Well, that's because they are in fact walks. A walk is a path in which you can revisit nodes. So you could go from A to B to C, back to B, back to A, back to over to B, over back to C. You can go back and forth, and that way you could have an infinite walk. Now, these matrices that count the number of k step paths or walks are weighted by these betas. Let's assume that beta is fractional. So it's between 0 and 1. So let's say it's something like 0.8. Then we've got 0.8 to the 0, that's 1. 0.8 to the first power, that's 0.8. 0.8 to the second power, that's squaring it, that's 0.64. 0.8 to the third, 0.512, 0.4096. As you can see, as that exponent gets larger and larger, the value of beta of the exponent goes down to 0. So when we're summing up all these matrices that have these infinite length paths, they're also being weighted down by the betas. So let's put all this together. When we sum this matrix plus this one, plus this one, plus this one, add them all up, what we're getting is a new matrix that gives the total number of walks of all possible lengths that join every pair of nodes. So for a given pair of nodes, I and j, we know how many walks there are that go from I to j of all possible lengths, but they are weighted by the beta values, which we've assumed are fractional. And so really that means that they're weighted inversely by length, because the really long paths are going to be weighted by really small betas. So I'm going to call that sum R plus here. So if we look at what that is, that's simply the number of walks from I to j weighted inversely by their length. And then once you've got that, if we now multiply that by the column of ones, that just takes the row sums of this. And so we get our vector here. And so the way we interpret this beta centrality vector is that it tells us the number of walks that originate with I, node I, to the rest of the world, weighted inversely by their length. Row, thank you. I was going to say row, but it looked like a funny row to me. Okay.
So I just uploaded the slides as well, because I think for following it's sort of handy to be able to note on these things.
Yeah.
Because the formula is getting quite complex. So Moodle, I've put in there.
Okay, good. And there are actually a couple of slides different at the very beginning, but certainly from this point on, nothing has changed. Okay, let me click into my presentation. And so what do we conclude from this? Well, if we've calculated our beta centrality, then and a person and a node has a high score, that means that it's positioned in such a way in the network that there are many short walks connecting to node to all the other nodes in the network. And that in turn means that there's a strong possibility of influencing others. So for example, maybe these are trust ties. And so that means that node I, if they have a high score, has many direct paths to others, many people that trust them. And then they are in turn connected to many people who are also well trusted, and so on and so forth. So they're good influencers. Here is that matrix that we just painstakingly calculated. It's node by node. It's for this network over here on the right. And just showing that what we do is we simply, and so what that means is that Actually, from A to A, there are a number of paths. So you can go from A to C and then back to A, or you can go from A to C to E to D to C and back to A. So there are cycles here. Of course, the longer ones are weighted less. There are many ways to get from A to D. So from A to D is very easy to get to, and also to E. So quite a few short paths to do that. And if we sum these up, we get these scores here, and we can see that D and E are the most central in the network according to this measure. And part of that has to do with, if you look at E and D, they're very similar to G and F. They look like they would all have the same centrality, but G and F are connected to a node that has just 3 ties, whereas E and D are connected to ones that have 4 ties there. And so that pushes things a little bit in the favor of E and D. One way to think about the beta, by the way, is in terms of a probability of passing things on. So if we make beta very high, like 0.999, then A is very likely to send to C, which means, and they're also very likely to send to E, they're very likely to send to G, and that means that long paths will actually count because there's really a pretty good chance that it will get there. But if beta is small, like 0.5, then there's only a 0.5 chance of going this far, and then a 0.25, 0.125, 0.0625, and so on, and the chances of getting to J are quite low. Now, let's think about all the possibilities for different values of beta. Suppose we take the extremes. If beta is 0, what happens? Well, if beta is 0, and we've got our sum here, beta 0 to the 0 power is 1, and this is our adjacency matrix, and so that's fine. Then we have 0 to the first power is 0, so that's going to wipe this out. 0 squared is 0. So all of these terms go away. All we're left with is the adjacency matrix, and then we're going to take the row sums of the adjacency matrix. So in other words, when beta is 0, we get degree centrality. We simply get the number of direct connections that a node has. As B gets bigger, longer paths are given increasing weight. And then finally, the biggest it can be is it's just under 1 over lambda, where lambda again was that largest eigenvalue of the adjacency matrix. So, and when beta is as close to 1 over lambda as possible, but without actually reaching it, it turns out that beta centrality is exactly equal to eigenvector centrality. So if you make beta equal 0, you have degree centrality. If you make beta as large as it possibly can be, you get eigenvector centrality. And what that continuum is how much we weight long paths. So if we're imagining some kind of a process where we think that things like maybe very juicy bits of gossip will move from person to person to person, the chain will keep going, we would want a large beta to model that. But if it's something that we just don't think is very transmissible, you tell one person and it kind of dies with them, then we would use a small beta to model that. Now, how do we actually pick beta? It would be nice if we had a very strong theory. Maybe in physics, we might have a theory that says beta for a certain kind of phenomenon, maybe the spread of disease, will be equal to 0.235. But we don't have such strong theories in the social sciences. So it's very difficult to choose that ahead of time, although I think in many situations we might be able to say, well, it should be a large beta or it should be a small beta. But another approach would be to choose beta entirely empirically. So let's suppose that we have a network and I don't know what the kind of tie is, but actually, well, in this particular data set that I'm going to use, it discusses important work matters with somebody else. So who discusses important work matters with whom? And we also know about each of the people in this network. We know their supervisor's evaluation of their performance. That's called eval. And we also know how well they're compensated. We know their salary, how much money they make. And we might be interested in seeing whether centrality in the network predicts their performance. And you could think of supervisor's evaluation and compensation as two different measures of performance. One's kind of immediate and one's kind of long-term. So we would calculate beta centrality, and we'd have to pick a beta centrality to do that. It turns out that if we calculate the eigenvector centrality, we get a lambda of 10.97. So 1 over 10.97 is the largest beta that we could have. And we know that we could have a beta of 0. That would be equivalent to direct ties. So why not let beta vary between 0 and 0.091? We could take on 10 equally spaced values between them. And we calculate the beta centrality with each of these different betas, which gives us a different set of scores for each node. And now we correlate each of those sets of scores with our dependent variable, which is with the thing that we're trying to explain, and we pick the one that explains the best. So if we're trying to explain, for example, the supervisor's evaluation of performance, it turns out that a middling beta is the most highly correlated. So when beta is 0, which is degree, we can predict supervisor's evaluation with a correlation of 0.183. If we allow slightly longer paths, so friends of friends, we predict a little bit better, a little bit better, a little bit better, and this, we get to a peak here. And then as we let beta get even bigger, the correlations begin to go down until they go really far down. So it appears here that if we're trying to understand how well somebody performs as a function of their location in the network, we're best taking into account sort of medium length paths. You need to know more than just how many people are they directly connected to, but you don't necessarily need to know that they have these really long paths, 12 links away, 15 links away to other people. It's the medium ones that matter. On the other hand, if we're predicting long-term performance reflected in their compensation, it turns out that we're best able to predict when we use a large beta, meaning when we weight longer paths more. Okay. Any questions about that?
Steve, can I clarify something? So when you talk about paths, it's not only that they have long paths, but they also have circles, right? Because it's also going back and forward.
Yeah, because they're not really paths, because they're actually walks.
Yes, just
they're loops, they're cycles. Yeah.
Okay. Yeah.
And
Oh.
Well, I was just thinking, so what would that mean? What kind of process would be like that? And if you take, for example, a coin and watch the coin, maybe you can tag the coin with a GPS chip or something, and watch it move through the economy. It can go from person to person to person, and then it might come back to a person. It might go back and forth between a set of people. Certainly, it might stay within a small village and never quite leave that village. It could change hands many times. Other things probably don't travel that way. So, for example, if I tell you a story, it's very unlikely that tomorrow you will tell me the exact same story because you remember that I gave it to you. Now, what can happen, though, is that I tell you the story, you tell the story to somebody else, and then that person tells me the story. That could easily happen. So stories might work that way. Virus infections might not, because once I get a virus infection, maybe now I'm immune, so it can never come back to me. So on.
So I think one of the examples we were discussing at some point with the paper that we did is information that's added to the thing. So if you think about information flowing through a network, where I give information to Steve, who gives it to someone else, who gives it to me again, but there's added information to this when it flows through the network. So cumulatively added information. So that's a situation where actually this sort of walk is actually a good example, I think.
Yeah. It can also, of course, cause major problems too. So if you have these walks in the network, then a person could potentially hear the same information from many different sources, sometimes having been changed along the way, and other times not being changed so much because it was a shorter path. And so what they receive is conflicting perspectives on the same, what used to be the same fact. Also, in terms of things like emotions and attitudes, you can have, as we've seen in American politics, we can have echo chambers where people feed on each other, and they send out information and somebody else sends it around and it gets amplified and it comes back to them in amplified form. And now they're really angry about it, and then they send it out again and so on. Okay, this is just another example. This is the Paget and Ansel data where you have marriage ties among Florentine families during the Renaissance. And so we know the network of which families have marriage ties with which other families. We also know the wealth of each family. And so we might guess that being central in this network could have something to do with wealth, either as the cause or as the result. And we might want to test that, but we don't know which would be the best beta to do that. And so we calculate 10 different beta values going from 0 to the maximum possible and correlate each of those centrality scores with wealth. And it turns out that here, the very clear answer that the correlations go down as we allow longer paths. So apparently only direct ties to other families contribute to your family's wealth. There's an interesting aspect to beta centrality that requires a little bit of introduction. Beta centrality is very versatile, as you can see. But just by changing beta, you could get the eigenvector centrality, which we thought was a nice measure. We can also get degree, which was a very understandable measure. But there's a whole set of other applications that are really interesting. There's a field of study called experimental exchange theory, popularized by Cook and Emerson, Emerson being one of the people that was behind theoretical exchange theory in general. And in experimental exchange theory, people are brought into a lab and forced to play a bargaining game. And the bargaining game, reduced down to its simplest level, is just one in which people who are connected to each other have to allocate 24 points between them. So for example, you might come into three people are brought into the lab, and person Y on the left here finds that they are allowed to bargain with person X. Person Y on the right is allowed to bargain with person X, and person X is allowed to bargain with either one of the Ys. And so what happens is that Y will say to X, okay, we've got 24 points. The fair thing to do is I'll give you 12, you give me 12, we'll split it equally. And by doing that, we'll each maximize the number of points. And we'll do this for many rounds, and we'll accumulate many points. And typically, this is how people start. They start with an egalitarian approach. But eventually, people like X in that position start getting the idea that, well, I could offer 12 points and expect 13 in return. And Y could say, no way, that's unfair. But then X goes to the other Y and says, okay, let's trade at 12-12. And then the first X knows, okay, that wasn't a really good deal. I got 0 points. So the next time X says, I'll give you 12, you give me 13, the left Y accepts, and they make the deal, and it's the Y on the right that doesn't get any points for that. In this particular little network, what happens in the end is that X, eventually all the trades go 23 and 1, and X accumulates all the points. Okay. So the overall purpose of the studies was to understand how position in the network affects bargaining power, and they also threw other things in like psychological characteristics and gender to see if how they interact with position. Like maybe men exploit their position more than women do, for example. That did not prove to be true, by the way. So if we take a look from the point of view of centrality, clearly in the first network here, it's a simple line. And by the way, they did not test only networks that look like lines like this. There were much more complicated ones, but it's very easy to talk about these, so that's what I'm showing you. X is the most central node, and we expect X to have all the power in the bargaining. And in this network down below, again, X has the most central position, and we expect them to have the most bargaining power. The numbers here are their centrality scores based on the eigenvector concept. And you can see X is the most central, the two Z's are the next most, and the Y's have the lowest. But what actually happens in the experiments? In the experiments, as I said, on the left network, everything works out just as we thought. X gets all the points. But in the one on the right, that's not what happens. What actually happens is that the two Z nodes get all the points. And Y, X, and the other Y have low points. Now, why is this? Well, it's because in bargaining, there's a couple of different principles here. One is that power is a function of having multiple trading partners. Y has only one potential trading partner. So in that sense, they're in the down position of a monopoly situation. No choice. Z has the ability to trade with either a Y or an X. X has the ability to trade with two different people, and Z, the other Z, has the ability to do that. So at least three of the nodes here have multiple potential trading partners. But there's more to it. The other aspect that's important is trading with weak partners. Now, in centrality, outside of these kinds of experiments, we typically associate, if we think about eigenvector centrality, we associate the idea that if you're connected to well-connected people, that means that you are supercentral. That means that it's good for you, right? But when it comes to bargaining, it's actually better to bargain with people who are in weak positions. So Z would rather bargain with Y, who is in a weak position, than to bargain with X, who would apparently be in a strong position. So we have to take into account both of these things. And actually, this kind of leads to a sort of odd and even rule, which is that if somebody, let's say you're Y1, if somebody is an odd number of links away from you, like Z1 is, they are one link away, that's an odd number, that is good for you because that means that's a potential trading partner. So let's give Y1 a point for that. But suppose there is an X that is two links away from you, an even number. Well, that's bad for you because it means that the person that you were going to trade with has an alternative to you. They could trade with X instead of you. So having a person two links away is always a detriment. Now, what about having a person who's three links away? Okay, so now we have Y1 has a point for being having Z1 there. They lose a point for having X two links away. And then they gain a point for having a person who's three links away, which is an odd number. Okay, and then, but that person, that was a great advantage, but this person has an alternative to that, which is somebody who's four links away from you. And so it ends up that you had 2 points for odd numbers, and you had taken away 2 points for even numbers, and so your score is 0. We can contrast that with Z1, who has 2 people that they can trade with directly, so that's 2 points. Fortunately, one of those people has an alternative to Z1. It's an even number, so we subtract 1 from that. But then we get that back again because there's a person who's 3 links away. And so that's a sum total of 2. And so it turns out that that one's in a good position. And the X, when we work out the same arithmetic, turns out to have a 0 because they have 2 direct links and then 2 alternatives to them, 2 even numbered ones. And so they end up being in the same weak position as the Ys. So this means that in competitive situations like bargaining, centrality is not always a benefit. But beta centrality to the rescue. Because although we hadn't mentioned it before, beta can be negative. Excuse me. So let's play it out here. Suppose beta is a negative 0.5. So here we have a negative 0.5 to the 0th power. So we've just got 1. And we've got here beta to the first power, that's a negative 0.5. Then beta squared, that's a positive, right? Positive 0.25. And then the odd numbered one here, beta the third, is a negative. And notice that that's playing out exactly the pattern that we were talking about before. So you get positive points for being an odd length away, but for people who are, for paths that are an even number of links away, we subtract that. And again, for ones that are odd numbers, we add that. The numbers keep getting smaller because they're getting larger, but the pattern is that whenever you have an odd number of links away from somebody, that's good for you, and when it's an even, it takes away from you. And so if we calculate beta centrality with a negative beta on the 2 networks here, we get, as expected, that X gets big points, and in the one on the right, X gets low points. Now, experimentally, actually, this isn't quite right. Experimentally, the Ys and the X's are indistinguishable from each other. They're just low power positions, whereas the beta centrality would suggest a particularly weak X. But still, it's in the right direction. It predicts pretty well. So again, very versatile measure. That's where my closeness went. Okay, so we've talked about closeness, so I'm just going to move on. Oh, but I did take advantage at this point here to, we had that data set where we've got supervisor's evaluation, we've got the compensation of each employee among the 331 employees. And so I was just curious as to which centrality measure would predict their performance better. And we haven't talked about most of these, but you see degree, you see beta centrality, you see eigenvector there. And then we have closeness. And it turns out that closeness is actually the best predictor of compensation. And let's see, is it any good at predicting supervisor's evaluation? Actually, it is. I mean, it's pretty high correlation there relative to all the others. There's certainly other measures, such as betweenness, that we're going to talk about in a minute, that are not as good predictors. So somehow, this is saying that if you are in a position in the network where you're not that far from all the other nodes, you tend to be a better performer. And that's particularly true in terms of predicting your long-term performance. Okay, betweenness. Oh, I should pause. Any questions?
So Steve, just to say, we have 35 minutes left.
Ah.
Just in case you want to skip over some things.
Yes, thank you. I will do that.
What I think is really interesting as well is the induced centrality measures.
Yeah.
Just to say, if you could get there, that would be great, because that's some of the things I think which are, is interesting, and it's sort of a different thing. So I can go over betweenness if for some reason you think you can skip that, but up to you.
Yeah. I will say just enough of it so that we can talk about the induced centrality, because I use it in that. So betweenness is the property of being in between others. So it means being along the shortest path between others. So for example, if you're looking to go from S to T, there are some short paths and there's some longer paths. And so P does not get any points for being along the way from S to T because it's a long path. But Q does, because this is a short path, and so does X because that's a short path. So basically we would give actually a half a point to each of them. So people get high betweenness scores if they are along the shortest paths between pairs of others. Okay, so now we're going to run over to induced centrality. And there's a handy little guide here about which measures work well for different kinds of networks, such as directed, undirected, and so on. So in induced centrality, this is easier than it's going to look. It's going to look as complicated as beta centrality, but it's not. So we said that centrality could be seen as importance. And often we take that to mean something that benefits the node whose centrality we're measuring. So it's an advantage to be highly central. But importance can also mean contribution to the network, like as in the sense of how different would the network be? How different would its structure be if that particular node were taken out of the network? How much would it affect things? And so that's what the measure does. So the way it works is we start out with some network level statistic. These are called graph invariants in this context. And a graph invariant just means that it's any statistic that depends solely on the structure of the network. It doesn't depend on who is in the network, whether they're male, female, or whatever, but just the structure. So an example of a graph invariant is the average distance between all pairs of nodes. Another one might be how centralized the network is. So what we do is we measure that first. Now we remove a node whose centrality we're measuring, and we recalculate this graph invariant. So we take the node out, and we recalculate the average distance between everybody, and then we just subtract. We take the value with everybody in the network, and then we calculate the average distance when we've taken node X out of the graph. The graph is G here. And that difference is called the induced centrality of node X. And we simply compute that for every node. Okay. So it's a very simple concept. It's just how much do things change when I remove this node. So an example of this is fragmentation centrality. If we look at a network like this and I measure how many pairs of people can reach each other by some kind of path, it actually turns out that every node here can reach every other node. And so there is no fragmentation. If C could not reach Q because there was no path, then there would be some fragmentation in this network. Now, what happens if we remove a node? I could remove G and recalculate for all pairs of nodes how many nodes can reach each other, and it's still the same. It's still 100% of the nodes can reach each other. There's zero fragmentation. I could remove node R, and that would be true. But things change with H. If I remove H, then the entire left-hand side is disconnected from the right-hand side, and R is also disconnected from the world. So there's a lot of fragmentation, a lot of pairs that can't reach each other. And that's what's shown in this first column over here. It's the fragmentation that results when you remove a node. You remove A, no fragmentation. You remove H, you have the highest possible fragmentation. I is next. There's also M here. If you remove M, that separates this little group from that group. So that introduces a certain amount of fragmentation, and the same for Q. We could also look at the change in the amount of fragmentation. These are all details that we don't really need to get into. But for example, it might have been that we started out with a network that had a certain level of fragmentation. And so what we're trying to really measure is how much increase in fragmentation there has been when we remove a node. But since in this network, originally all the values were 0, there's no difference between fragmentation and the difference in fragmentation. We could also take it as a percentage change. But anyway, we'll leave that for the moment. So before we actually give an example of it, I want to point out one of the great qualities of induced centralities. And one of those qualities is that you don't have to use it for just calculated centrality of one node. You could ask what happens if I remove these 2 nodes, and if I remove those 2 nodes and this other pair of nodes, and you could figure out, well, which pair of nodes would cause the greatest amount of damage to the network if they were removed. And of course, it doesn't have to be pairs of nodes. It could be all the nodes of a certain characteristic. So if we have a large organization and we have some statistic, let's say the statistic is the number of pairs of nodes that can reach each other by a path of 3 or less. What happens if we were to take out everybody who was in the marketing department? Now, how much does that change the connectivity of the network as a whole? What about the accounting department? And so on. So in other words, we could measure the centrality of each department by measuring how much it changes the network if you were to remove that department. It's also obvious that we could use induced centralities to calculate the centrality of ties. So we could see whether some tie is particularly important, as in this network here, the tie from I to H, that friendship there, that trust is very important, because if that goes away, none of these people trust any of the people over on the right, and we have issues until new ties can be built across the groups. The other thing that I guess should be clear is that we can do an induced centrality with any statistic we want. Any statistic we want to invent, any measure of cohesion of the network, for example, we could use that as the basis for constructing our induced centrality. So given that we can use anything we want, let's do something perverse. Let's start with a centrality measure that already exists, such as the betweenness centrality, right? So B of X means the betweenness of node X, and so we'd have a score for every node. So we take that, but now what we do is we sum the betweenness scores for across all nodes for the entire network, and that becomes our graph invariant. Okay, it's the sum of centralities of everybody. And by the way, if that sum is large with betweenness, that would indicate that every node is highly between, which means that it's kind of a brittle network. Every network, it's almost like every node is quite important, because if you remove them, then the shortest path is a longer path between any pair of nodes. So it's kind of an interesting statistic. So what do we do to calculate our induced centrality? We sum the between the scores for everybody. Now we remove X. We recalculate between the scores for every node that's remaining. We sum up those between the scores, and that gives us the graph invariant for the network minus node X. And to calculate our induced centrality, we simply subtract that, right? So we see how much does the sum of between the scores change when we remove node X. That's what this is. So one question we can ask is, okay, how does that relate to the betweenness of X? I mean, we already had a centrality score for each node, but then we summed them up, and each node contributed betweenness to that sum. Then we removed the node, we summed up all the betweennesses, and how much does the network change when we remove that? So you might expect that this induced centrality would actually be the same as the betweenness, because that's how much you contributed to the sum. Each node contributed their betweenness. But it doesn't quite work out that way. And let's just introduce some terminology to think about it. Let's call the off-the-shelf measure centrality, like betweenness, let's call that the direct contribution of the node, right? It's what went straight into calculating the graph invariant. We can also call it the endogenous centrality of the node. So the graph invariant then is going to be the sum of all these endogenous or direct contributions. The difference, the induced centrality here, that's the induced centrality. We might call it the total centrality. We'll come back to that. Now, what's interesting to look at is what's the difference between the induced centrality, this one, and the endogenous centrality that we use to construct it in the first place. We'll call that the remainder, or exogenous centrality. I like to think of it as the indirect contribution. So let's just be clear before I show the next slide. The induced centrality is how much the sum of betweennesses changes when you remove node X. The endogenous centrality is the betweenness of node X that was used to calculate the induced centrality. And then there's some difference, possibly zero, which is over here. So let's take a look at a network here. Here are Florentine families. And we've got the endogenous centrality of each family. Okay, so that is the betweenness centrality that we would calculate from the software directly. The Medici have a high score of 48. They're right in between many paths in the network. They're very important. Some nodes have zero betweenness centrality. Nobody needs this Ginori here to get to anywhere else, right? The Albizzi have a little bit of betweenness because the Ginori need the Albizzi to get to everybody else in the network. So now we sum this column up and we get the sum of betweennesses. Then we remove each node, we remove the Medici, and we recalculate betweennesses, sum it up, look at the difference, and we get a difference of 73. So what that means is that the Medici contributed directly 48 points to the sum, but when you take the Medici out, it reduces the sum by 73, meaning that they were contributing indirectly betweenness centrality to others. So, for example, if we look at Salviati here, they have some betweenness because Pazzi needs Salviati to get to Ridolfi and so on. And so if the Medici were removed, then that would no longer allow the Salviati to get any betweenness points, because nobody needs the Salviati family to get to anywhere, since it would just be a line between Pazzi and Salviati here. So the Medici have betweenness of their own, but they also give betweenness to other nodes. And how much they give is 25 points worth. Some nodes, actually, Salviati is one of them, actually give to others much more betweenness than they directly contribute. So their direct contribution is only the fact that Pazzi needs them to get to the rest of the network here. But all of these nodes over here all need Salviati to get to oh, that's the same thing actually. But if we take it away, then the Medici become quite a bit less important, because again, they're not needed now by the Pazzi family or these guys to reach everybody else. You can also have the situation where it's a negative contribution. So the Ridolfi here, they contribute 10 betweenness points to the sum, but when you take them away, the total sum is only changed by 9 points. So they were actually acting as a suppressor and reducing the betweenness of others around. How were they doing that? Well, because they were providing a direct link. So the Medici here were using the Ridolfi to reach the Strozzi, but that's actually well, if they hadn't been there, they would have to go this way. No, that doesn't work. So the Salviati would need the Medici to get to the Strozzi, and the Ridolfi are shortening that path. Let's see if the Ridolfi weren't there. I'm getting myself confused. Philip, can you see how it is that by shortening this path, it is...
So the Ridolfi actually, if they would not be there, they would give more betweenness to others. That's what it's saying, right? Rather than
Yes.
reduce the betweenness of others. So it actually would make the others more powerful, if you think about betweenness as power, of deciding whether information flows because of that. Whereas in the other cases, they actually contribute to the betweenness of others. So it's here, it's the Ridolfi. If the Ridolfi are not there, I think that they actually increase the betweenness of other people. I mean, that's basically what it's saying, right? It's increasing the betweenness of other people if they wouldn't be there. Or is the opposite? Now I have to think about it as well. We'll come back to this anyway. I'll try to next time. I'll maybe not next week, but in a few weeks I'll come back to this, because it's an interesting aspect. But yes, so it's doing the opposite in what you would expect.
But yeah, but that can't be right. It is literally that they are they are harming the betweenness of others. And you can see that the ones like Pazzi here, they have no betweenness of their own, but they contribute a lot of betweenness because they make Salviati have a role. If Pazzi weren't there, then Salviati would not be between anybody. And so that's why the Pazzi have a big number. They contribute to others. And this negative means that they contribute negative points they take away from others. But anyway, I will quickly just do one quick example using the data that we have already been looking at. I'm going to predict, let's see, compensation and valuation data. Let's see what I actually use. I used compensation, and I'm predicting it as a function of their age, whether or not they're women, whether they're located in the Singapore office, whether they're a manager or not, and so on. And I'm adding one variable here, which is the exogenous centrality. In other words, that's the amount that they contribute to others' centrality. And it turns out that in the regression, what we see, it's significant and it's in the negative direction, which means that apparently if you contribute to other people's centrality, you're a good citizen, it harms you. You get paid less. That's an unfortunate result. Okay, that was it. I'm still stuck on this.
Well, we will come back to this in a few weeks, Steve. I think we will we'll talk about it, and then I will make sure that we come back to this. But thank you for explaining this already. This is one of the papers that you did a few years ago, right?
Yeah.
So what's interesting about this is really that from a sort of theoretical perspective, it's showing that if you think about betweenness as having power of, you know, negotiating between people, or it's flowing, information flowing through this, that it's not only that whether you are the person that's a broker between others, but also it's not only that you have a position, but that actually also you're offering other people some benefits or some disadvantages with the -1 of making them being between or not being between, so being broker or not. And that's the nice thing about, you know, thinking about the group. It's not only that you make yourself powerful, but by doing that, you might actually also make other people powerful, or you might reduce their power in some ways. And so thinking about it from a social science perspective, to sort of, you know, what are you doing not only to yourself, but by doing this, what are the unintended consequences, so to speak, of your position? Yeah. Steve, did you want to say anything else on this? Because I wanted to say one more.
No. I'm stuck on how to explain
Okay.
it.
Well, you know, if you're, that's the loop thing. One other thing is, so I was thinking about key players, and okay, I haven't told anyone about key players yet, so I know that this is going to come back, but it seems to be sort of related with the. I'm going to come back to this, so students, please don't be panicking about this thing, but it's related with the key player question in a negative way, right? A negative key player thing as well.
Yeah.
Or not. So let me bring it, maybe let me talk about one other thing. So it's basically, think about if you have a mafia or a criminal organization, and as a government, you want to destroy this organization. You want to, you know, make it really split up into groups so that they can't communicate with each other. Think about 9/11, but also think about mafia, think about any criminal organization. If you can target one person and remove them so that this network disappears, or, you know, becomes fragmented, which person would you choose is one of the questions you could ask. And this is related with the key player question, which I'll come back to. I don't want to spend too much, you know, introduce more things, but is that correct, Steve? That it's sort of.
So, I mean, one way to look at it is that if we're only interested in removing the one player, then key player is exactly the same thing as fragmentation centrality here. And so we would say, okay, H clearly is the one that if you remove it, maximally fragments.
Yeah.
But what if you had the resources to isolate or arrest two people? Which two people would they be? The naive answer is you would pick the two most central individually and you would remove those two. But actually, if you did that, having removed H, removing I doesn't fragment the network any more than just H alone. So really what you want is to pick somewhere over here. Actually, if you were to pick H and M together, even though M individually is not so important, the combination would do a lot of damage to this network. And that's what key player does, is that it says, okay, what is the best set of K key players to remove, such as to most disrupt the network? Or the positive version, or is to improve the connectivity in some way.
Yeah, great. So I'm just mentioning this already. We'll come back to this, the key player question, and, you know, so don't worry at the moment. We'll come back to this concept, but there is a link with that as well. That's sort of interesting. Yeah. Okay, good. Are there any questions?
What's going on with Ridolfi?
um, it's something where you need maybe like, yeah, it's a homework for students as well.
Yeah.
For next week, try to find out what happens with Rodolfo. Someone will find it, I'm pretty sure.
Yeah.
Okay, great. Well, Steve, thank you for this. I think it's a real great opportunity to see the diversity of centrality measures that we're that are available there, and we're going to come back to this partly also with looking at Steve's 2005 paper. I think it's 2005 on flows and different types of flows. So, different centrality measures. When do we look at gossip? When we look at gossip, for example, what's different from if you look at money flowing through the network versus a virus, where the virus can go, infect you again, or the virus cannot infect you again, or an email communication. So we will come back to this in more detail. So if there's no other questions, I would say we've seen a lot of things. And as I said, I'm available also next weeks and the weeks after to really talk about in more detail about these things. If there's something like the beta centrality, which is really challenging, and we're aware of that. So have a look at this again. And then tomorrow, as I said, we have our class. So I will see you tomorrow with your computer, or we'll organize the online session, and that's normally next week, Tuesday.
Yeah, I figured it out.
Oh, okay. So no, don't
Peruzzi.
go.
Look at Peruzzi. So they have to get to places like the Medici, okay? So they can go through Strozzi. Strozzi gets between his points because there's a path this way, 1, 2, 3, and then there's an equally short path this way, 1, 2, 3. So Strozzi gets points for that, but only because Ridolfi is here. You take away that one, and then the shortest path is going to be up this way, and Strozzi gets no between his points for that. So Ridolfi is a spoiler. They're actually taking opportunities for being between away from Strozzi.
Okay, good.
I know it wasn't as exciting for you as it was for me, but okay.
It is, yes, it is, but it is interesting to see this. So yes, so Steve, many thanks. I think it's lunchtime for you, over
Yes.
lunchtime. So have a great lunch. Thank you. And I think the students are, I know they were happy about the fact that you were going to give a guest lecture. So thank you again.
Yes, and then they were unhappy when they discovered beta centrality.
Well, that's not your fault. That's the fault of, that's Bonakic. That's not you.
The bonuses, yeah, right. Okay.
Okay, well,
Bye all.
thanks everyone. And we'll see each other tomorrow or next week on Wednesday. Yeah, so tomorrow we do pictures.